Hello, my name is Vimal Rao, and along with my colleagues Dr. Jeffrey Bai and Dr. Shashank Varma, I explored the way that individuals process p-values. In 2019, the American Statistical Association issued a statement on p-values in which they decry its dichotomization into statistically significant and not statistically significant. They go even further and recommend that we should no longer say or use these category labels and dream of a world beyond p less than 0.05. These decisions are in reaction to what has become a full-blown controversy, with some journals even banning the use of p-values, and some strongly advocating that they be excluded from submissions. Despite these deleterious effects, categorization can be helpful, especially for novice learners. However, categorization can also fundamentally change the way we reason about stimuli. It's that question that we explore here. As a 0.05 boundary for p-values has been traditionally emphasized in statistics instruction and practice, has this categorization resulted in changes in people's understanding and processing of probabilities? I'll start with an example of how categorization can change the way we process stimuli. This phenomenon, known as a categorical perception effect, has been extensively studied in the speech and hearing sciences. Consider the sounds sh and s. In the English language, we have separate phonemes for each of these sounds. So long as I say something close to s, you will understand that it is s that I'm saying. But how would we process a series of sounds on a continuum between sh and s? I'll play an example of these now.
Sha, 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 sha.
That went by fast, so let's do it one more time.
Sha, 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 sha.
Perhaps you heard that the first sounds were very much like sh, and then there was a sh-s mixture, and then the last few were close to s. However, these sounds were actually all equally spaced on the phonetic continuum between sh and s. The theory of categorical perception explains this phenomenon as follows. The existence of sh and s phoneme categories serves to exaggerate the perceptual differences between exemplars from each category, while minimizing perceptual differences among exemplars from the same category. Might the categories statistically significant and not statistically significant have a similar effect on probabilities as p-values? To answer this question, we first have to consider how individuals process numbers. Evidence from mathematical cognition suggests that we have a mental representation akin to a number line. For example, we're faster at selecting the larger of two numbers when the distance between them is greater. This is the distance effect. However, our mental number lines are not linear or evenly spaced. Consider the difference between 3 and 2 compared to the difference between 7 and 6. Both are only 1 apart in a linear scale, yet we're generally faster at indicating that 3 is larger than 2 than we are at indicating that 7 is larger than 6. This is called the size effect. This, and other effects, suggest that the mental number line is logarithmically scaled, because the mental distance between 3 and 2 is larger than the mental distance between 7 and 6, as it is in log units, explaining the faster response times. Another line of research has shown that place values affect numerical judgments. In multi-digit numbers, our ability to find the midpoint between two numbers is impaired when those numbers span multiple decades. For example, finding the midpoint between 29 and 35 is harder than finding the midpoint between 31 and 37. This is the decade crossing effect. These results, while predominantly studied using integer stimuli, have also been extended to proportions or decimals between 0 and 1, which is where the p-value continuum lies. Based on these theories from the mathematical cognition of numbers, where numbers are understood purely according to their continuous magnitudes, our null hypothesis is that statistically significant is simply a label for p-values, with no effect on reasoning. If so, the logarithmic mental number line will accurately predict how participants respond to stimuli as probabilities. However, we predicted that this null hypothesis would be wrong, and that the statistically significant and not statistically significant categories have altered how participants process p-values much in the same way the sha and sa categories have altered how people hear word sounds. The key question is thus whether, after controlling for other known effects, participants perceive an exaggerated difference between p-values when they cross the 0.05 boundary. We recruited participants from the pool of graduate students in the Department of Educational Psychology at the University of Minnesota. Eligible participants were those who have completed at least 1 year of statistics instruction at the graduate level. 25 eligible volunteers thus participated in the study. We hypothesized that these students' exposure to statistical instruction, reading of research papers, and research talks, all heavily utilizing these 0.05 statistically significant conventions, would have reinforced the students' categorization of p-values, which in turn would affect their reasoning about p-values. To assess whether these experiences with the 0.05 boundary lead to exaggerated differences, we utilize what is known as the AX discrimination task from the categorical perception literature. We first presented participants with a single p-value. After 1 second, they were then shown a second p-value and asked to indicate whether the two p-values were similar or different. No guidance was given as to what criteria they should use in making these judgments. The experimental stimuli were thus pairs of p-values on different sides of the 0.05 boundary, such as 0.048 and 0.052. However, because of the decade crossing effect, we matched each of these 0.05 crossing stimuli with a pair of p-values that were both below 0.05 but still crossed the decade, such as 0.038 and 0.042, as well as a pair above 0.05, such as 0.068 and 0.072. This allowed us to control for a baseline decade crossing effect as well as a size effect, enabling us to identify any exaggerated differences when crossing the 0.05 boundary, beyond what occurs for the other decade boundaries. We also systematically varied the distance between and size of the stimuli to control for distance and size effects. In total, 108 p-value pairs were presented to participants. We first analyzed the frequency of participants' different selections as a function of the distance between the stimuli and whether the stimuli pair was below 0.05, above 0.05, or 0.05 crossing. Let's consider the predictions that the log mental number line makes. Again, this can be regarded as the null hypothesis. Due to the distance effect, as the distance between stimuli increases, the frequency of different selections should also increase. Furthermore, due to the size effect, the frequency of different selections should be highest for the stimuli below 0.05 for a given distance, and the lowest for the stimuli above 0.05, with the frequency for the 0.05 crossing stimuli somewhere in between. However, a potential categorical perception effect suggests that it is the 0.05 crossing stimuli that will have the highest frequency of different selections for a given distance, and that the frequencies for the above 0.05 and below 0.05 stimuli will be similar. The key question is thus, where are the relative frequencies of different selections for the 0.05 crossing stimuli in relation to those of the below 0.05 and above 0.05 stimuli? What we found was strikingly similar to the predictions of a potential categorical perception effect. We fit a log binomial mixed effects model to the data, controlling for the distance effect, size effect, and decade crossing effect. This model suggests that participants were nearly 2.5 times as likely to indicate that a pair of p-values were different when they crossed the 0.05 boundary. Furthermore, as expected, as distance between the stimuli increased, so too did the relative frequency of the different selections. This is akin to the distance effect. However, the frequency of different selections was not related to the size of the stimuli, akin to the size effect. This pattern, while unexpected in relation to the log mental number line, is consistent with the predictions of a potential categorical perception effect. We then analyzed participants' response times when selecting different to see whether they were faster at selecting different when the p-values crossed the 0.05 boundary. We did this by fitting a log normal model to the response times, again controlling for the distance effect, size effect, and decade crossing effect. Participants indeed were faster at making such selections by an estimated 275 milliseconds, compared to the model-adjusted mean response time of 1,114 milliseconds. This is a 22% reduction. These two findings, that participants are nearly 2.5 times as likely to indicate that a pair of p-values are different when they cross the 0.05 boundary, and are 22% quicker at making such difference judgments than in other cases, are consistent with the predictions that a categorical perception effect would make. These differences hold after controlling for standard mathematical cognition effects associated with the mental number line. We interpret this as evidence of a real cognitive difference, implying that training in statistics and psychological science appears to have induced a boundary at 0.05 in people's mental number line. As the debate and controversy surrounding p-values continues around us, these results suggest that some of the biases in the literature, such as the phenomenon of p-hacking, might partially reflect more automatic cognitive processing of p-values and not deliberate questionable research practices. This implies that in order to move into a world beyond p less than 0.05, we have to consider our cognition and the way it interacts with statistical reasoning and thinking. Furthermore, it suggests that we cannot simply move to other statistics and continue the same categorization practices, such as with small, medium, or large effect sizes. At the least, we believe that this evidence calls for more research investigating the underlying cognition associated with using p-values, especially in balancing the benefits of categorization for learning with their cognitive consequences. While there are several limitations to this study, such as the limited number of stimuli, the small number of participants, and the novel adaptation of the AX discrimination task to numeric stimuli, we're in the process of conducting further studies to continue to shed light on this phenomenon. For example, if our learning hypothesis is correct in that instruction and exposure to a literature still heavily influenced by statistically significant p-values, the more training and experience one has in statistics within our research context, the more prominent the 0.05 psychological boundary might be in their mental number line. We are currently testing this hypothesis in another study. Ultimately, we hope that this line of research will lead to new methods for teaching and practice that support our move into a world beyond p less than 0.05. Thank you very much, and please contact us for more information about this project.